Professor Jovanovic is here. Yeah.
Hey guys.
Hi.
Hi, Mihailo. How are you?
Hi. Can you see me?
Yes.
Excellent. Hey, great to see everyone. Thank you so much for setting this up. I really appreciate the opportunity to give a talk. It's an absolute pleasure. Thank you.
It's our pleasure.
Thank you for coming.
Yeah, our pleasure.
How's everything going?
Pretty good.
You guys are staying strong even in these non-trivial times?
Yeah, kind of. I mean, staying home.
Yeah, same for, actually, I came to my office today. I came to my office because I was concerned that my internet connection at home may not be good enough, because my kids are attending their school from home, and then, you know, this is causing lots of internet traffic. So I didn't want to run into any trouble. So here I am. Our campus is a complete ghost town. There are no human beings anywhere in sight.
So how's the weather in LA?
It's a little bit cloudy because of all of these fires that have been happening. To be honest with you, you guys put so much pressure on me to prepare this talk that I haven't left my house in the last couple of days. So I can't really answer. The question with complete certainty. So I never gave this entire talk before, so I had to invest some additional time into preparing it. So we'll see how it goes.
Great.
Yeah. So who's going to introduce me?
I'm going to introduce you before the talk. And
good.
So during the talk, we will not interrupt you, and you will give the whole talk. And after that, we will collect all the questions raised in the Q&A section and pass them to you after the talk. So there will be a Q&A section. Okay.
So how much time do I have?
It's up to you. So normally the talk will last for 15 minutes or 45.
Okay. No, I'll plan to finish within 45, 50 for sure. Especially since you guys are not going to interrupt me. I'll give my best to wrap it up within 50 minutes so that we have enough time for discussion. Can you just clarify for me how to pronounce your name? Zoran, is that
Joran.
Yeah, that's accurate. Yeah.
Joran.
Yes.
Okay,
Jordan.
you're almost like Jordan, Michael Jordan. I'll call you MJ, Jordan. Joran. Okay.
Yeah. Also, I would like to see if I pronounce your name correctly. So is your name Mihailo Jovanovic?
Mihailo Jovanovic.
Mihailo Jovanovic.
Jovanovic, yes.
Jovanovic.
You can introduce me like Michael Johnson if you if you translate my name to English, it's Michael Johnson. So it's much easier. Don't worry about pronouncing my name, man. People slaughter it all the time. So
yeah, I even Googled it how to pronounce your name.
No, man, I put way too much pressure on you. So I need actually to bring you out for beer once we finally meet each other in person to compensate for all suffering that you went through. To me, it's funny actually when my students, after working with me for 4 or 5 years, they go to a conference and they slaughter my name, and I'm like, man, that should be at the very least requirement actually for being a member of my group to practice how to pronounce my name. But
you're not talking about Dongshen, right?
No. Actually, Dongshen is pretty good. My former student Armin, so he was even my postdoc, and then he goes to a conference and he says Jovanovic, and I'm like, man, you've been working with me forever. You should by now recognize that Serbian is phonetic language, that J is Y.
Yeah.
So anyway, but man, I already forgot how to pronounce your name. So yeah. So I see that you guys have lots of exciting speakers. So this is really phenomenal.
Yes, we are fortunate to have a list of high-profile speakers.
No, good. Kudos to you. That's a great thing. Shall I attempt to share my screen to see if the slides are going to?
Yeah, we can also see your mouse, so you can illustrate things using.
Excellent. So can you see this now? Can you see my slides?
Yes, yes. Maybe you can.
Excellent.
Try to do the full screen.
I did this full screen already, actually.
Oh,
no, it's the
But
slides
we can
to be
There's
full
a presentation. Yeah.
yeah, we can see the toolbars on your screen.
So what should I do? Can you give me some advice?
Can you open by preview? That is usually easier.
If you are using a MacBook, then
Yeah.
you can try.
So it's easier to use than
Adobe.
Acrobat.
Yeah.
Right.
Yeah. Yes.
Yeah.
Okay. So let me. I never attempted that before, but let me try to. Okay. So preview. Okay. So let me try to share screen now again. Just a moment. So now I lost Zoom for whatever reason.
So is it?
So what should I do? What should I do?
Can you have a new share screen? Click the new share screen.
I see. Here it is. New share screen. Okay.
Yeah. Oh yeah. So now your system is a little bit different than.
Oh man, I don't want to do this. This is let me try actually to open PDF in Acrobat.
Okay.
I think this is a little bit. See, I never tried this before in preview via Zoom, so I don't want to. Oh shoot, man! What the heck happened here? Let me compile this again real quick. Just a moment, guys.
Sure.
Just bear with me for a moment.
Sure. Take your time. There's pretty lot of time left.
Yeah.
Yeah.
Okay, so let me try to open this now. Okay, so let me try to share screen now. Share screen. Is this okay now?
Yeah. Perfect. Yeah.
Perfect. Yeah.
It looks good?
Yeah.
Excellent. Okay, so let me just step out of my office real quick. I'll be right back. I need to turn on lights and
Sure.
to take care of a couple of additional things, and I'll be right back with you guys in a moment.
Sure.
Okay,
Take your time.
sounds good. Thank you.
Okay.
Still everything okay with the screen? You guys see the slides?
Yeah,
excellent. Thank you.
Yes,
it's working.
Great. So we will begin at around 3:02, giving a few minutes for the audience to join.
Just take your time.
Jordan, let's start.
Okay, sure. Hi, everyone. Welcome to the online seminar on the mathematical foundations of data science. Thank you all for joining today. Our seminar is generously sponsored by 2 Sigma. It's my great pleasure to introduce our distinguished speaker today, Professor Mihailo Jovanovic from the University of Southern California. Professor Jovanovic is a professor in the Department of Electrical and Computer Engineering and the founding director of the Center for Systems and Control at USC. Professor Jovanovic has made fundamental contributions to distributed optimization, control theory, and dynamical systems. He is a fellow of the American Physical Society and IEEE. He has received many prestigious awards, such as NSF Career Award, the George Axby Outstanding Paper from the IEEE Control System Society, and an Early Career Award and a Resident Fellowship Award from the University of Minnesota, and the Distinguished Alumni Award from the Department of Mechanical Engineering at UC Santa Barbara. And his papers of his students were finalists for the Best Student Paper Award at the American Control Conference in the year 2007 and the year 2014. He has also served as the associate editor of the IEEE Transactions on Control of Network Systems, SIAM Journal on Control and Optimization, and IEEE Control Systems Society Conference Editorial Board, the chair of the APS External Affairs Committee, and the program vice chair of the IEEE Conference on Decision and Control. The title of Professor Jovanovic's talk today is Policy Optimization for Linear Optimal Control with Guarantees of Robustness. Please join me in welcoming him.
Thank you, Joran. Thanks for this generous introduction and for your kind invitation to speak in this exciting seminar series. You guys have been doing tremendous service to the entire community, and I'm grateful for the opportunity to speak here today. As you mentioned, I'll be talking about convergence and sample complexity of gradient methods for the model-free linear quadratic regulator problem, and this is a work done by my PhD student Hessam in collaboration with my former student and postdoc Armin and my friend and colleague from USC, Magdi. So as probably everybody in this audience knows, a grand challenge in the area of reinforcement learning is how to design controllers potentially for complex dynamical systems that operate in uncertain environments in the absence of first principle models. So absence of first principle models is perhaps the biggest differentiating point relative to the approach that is typically taken in control theory. But on the flip side, you have access to the abundance of data. And then the question arises how you can strategically utilize data to learn controllers, perhaps online, and at the same time guarantee a certain level of performance. And obviously there are tremendous success stories in recent years that have attracted not only attention of scientific community, but also caught and captured the imagination of a broader public. And these success stories range from the area of robotics to the areas of games where tremendous accomplishments have been made. However, as these techniques are being brought from carefully controlled environments, perhaps from environment in which you simulate your dynamical system, to an environment where you need to have performance and safety guarantees, the question is, can we really guarantee safe performance in uncertain environments where there is no wiggle room for error? Or at least can we do that in a similar way that we typically do in control theory, for example, in the area of aerospace engineering, where safety guarantees are very strict and where there are well-established practices for achieving these. I typically hate pictures like this, and they are displayed on the first couple of slides without ever coming back to them, and I'm not going to deviate from this standard practice. So, but keep in mind that as these techniques are being brought to real life, we need to have guarantees in terms of at least understanding how they perform and how they perform in the face of uncertainty and uncertain environments that these physical systems are facing. Today, I'm going to examine a standard problem in control theory, which is given by a linear quadratic regulator problem. And this is really the cornerstone of control theory. It has a 60-year-old history. It was solved back in 60s. And it involves minimization of a quadratic objective function for linear dynamical systems. So this buzzword, linear quadratic regulator, means that you're obtaining controller, namely regulator. Back in 60s, control community was aware of the fact that buzz names are important. Regulator certainly sounds more mysterious than controller. So you're obtaining regulator or controller as a solution of this optimal control problem, where you're minimizing quadratic costs. This is Q in this acronym, subject to linear dynamical systems. And there are many variations of this problem, but the simplest instance involves an infinite horizon cost for linear time invariant dynamics. And in my talk today, I'm going to focus on continuous time dynamical systems in which evolution of the state vector, X here is a vector of state variables, is governed by this first order ordinary differential equation, which is driven by a control input U and a random initial condition X naught that we assume to belong to known distribution. A and B here are constant matrices. For time invariant problems, they are fixed constant matrices. They are just given by a collection of constant numbers. And matrix A generates the underlying dynamics, and matrix B tells you how your control signal input that you would like to design in order to force your system to behave in a certain way enters into the underlying dynamics. Quadratic cost is given by this integral expression. In the simplest form, again, it involves minimization on an infinite time horizon, and it captures both state cost and control cost, where these matrices Q and R are positive definite matrices that respectively reflect state and control weights. And again, matrices A and B are model parameters that are in standard context perhaps obtained using first principle models. And as I mentioned, this is a standard problem that was solved back in the 60s by Kalman. And the optimal solution turns out to be given by a linear feedback policy, namely at any time instant, at any time t, you form your control action by acting on the vector of available state measurements, of the state measurements, by a fixed matrix K. So this matrix K, its dimension is determined by the number of components in the control vector and the number of components in the state vector. And at any time instant, you form your control action by multiplying vector X, vector of state variables, with this fixed matrix. And this fixed matrix can be obtained using celebrated algebraic Riccati equation. So Riccati equation is listed here, and it is a quadratic equation in this unknown matrix P. And under certain very mild system theoretic, control theoretic conditions that involved well-known controllability and observability assumptions, there is requirements, there is a unique positive definite solution to algebraic Riccati equation that determines optimal stabilizing feedback gain. Feedback gain that provides stability of the closed loop system and at the same time minimizes this quadratic cost in the presence of linear dynamics. So there are efficient linear algebraic and iterative techniques for solving this equation. We even teach this at the undergraduate level these days, because you can go to MATLAB type LQR and obtain solution of the previous problem, provided that you have model of your system. Namely, in order to solve algebraic Riccati equation, you need to know model parameters, matrices A and B, and you need to know state and control weights, Q and R. The challenge that arises in modern setup is what to do in situations where you don't have access to the model, where perhaps you can only have access to data, and one avenue you may want to take is to use data strategically to estimate these matrices A and B. Right, to do system identification if you want to, or to tap into the area of machine learning, utilize modern techniques in order to estimate matrices A and B and then compute solution of the algebraic Riccati equation. However, this is not the point of view that is adopted in model-free reinforcement learning. In model-free reinforcement learning, you would like to attempt to learn feedback policy by optimizing over the underlying feedback gains. Namely, you can express this quadratic performance index as a function of the feedback gain K, of the matrix K. And then the questions that arise in this context, if you perhaps utilize gradient-based optimization techniques to learn feedback policies, what are the convergence properties of gradient-based techniques or of your favorite optimization technique? This is a non-trivial question because it is a standard fact that I'm going to explain in a moment why this is so, that once you express this quadratic performance index as a function of the feedback gain, you lose convexity. And another challenge that arises, and another burden that you need to deal with, in the absence of models, you need to establish statistical properties of your optimization-based techniques. Namely, you don't have a luxury of having access to gradients. You can only evaluate function values, and then its relevant question is to quantify sample complexity of the underlying techniques. And in the next couple of slides, I'm going to tell you what our contributions in this area are, and in the rest of the talk, I'm going to guide you through these contributions and to compare to alternative techniques. So the first contribution that we made, we established global exponential stability. When I say global, over the set of stabilizing feedback gains for the gradient flow dynamics for the linear quadratic regulator problem. Namely, once you express LQR cost in terms of the feedback gain matrix, you can use gradient flow dynamics, and in spite of the lack of convexity, we managed to show exponential stability, which is the strongest form of stability you can hope for in this context over the set of feedback gains that provide stability of your controlled system. The reason why we are focusing on gradient flow dynamics is because it's a little bit cleaner than studying gradient descent, but it turns out actually that standard gradient descent technique that can be interpreted as a forward Euler discretization of the gradient flow dynamics with small enough step size alpha also achieves linear convergence over the set of stabilizing feedback gains, which is an equivalent of exponential convergence for ordinary differential equations. So the first question on this list in terms of convergence properties, even when you have models, has been settled down by our recent work for continuous time LQR problem, both for gradient flow dynamics and gradient descent. Another contribution that is perhaps more relevant for this audience is that we quantified, we address convergence behavior and sample complexity of the random search method for the linear quadratic regulator problem in continuous time. And what we managed to show is that you can achieve desired accuracy at a linear rate, again, over the set of stabilizing feedback gain with logarithmic complexity, logarithmic sample complexity, or logarithmic number of function evaluations, if you want to, with respect to the reciprocal of the accuracy. And I'll be very precise what I mean by random search method. What I would like to highlight is that all of our results in the second part, in terms of using random search method for model-free LQR, hold with high probability, and all details in whatever I'm going to present today are contained in our archive preprint that is also, that has been conditionally accepted for publication in IEEE transactions on automatic control. What I would like to highlight is that in model-free setup, we do everything offline. So if you expected regret type bounds and these type of results, you're not going to see any of them today. So we do everything online. We design numbers that comprise feedback gain matrix K in an offline fashion, and then we would implement this on a real physical system. And in terms of the structure of my presentation, I'm going to do things upside down. I'm first going to actually tell you what we've done in the model-free context, because I feel that this audience probably has much more interest in this topic, and then I'll go back and show you how we establish properties even when we have models. So the reason why I inverted these things, in addition to the fact that probably more of you care about second part of the talk, is because first part of the talk is, our first contribution is a little bit more technically involved and involves heavier control theoretic components, so I didn't want to kill everybody early on. I want you to be focused at least for the first 20-25 minutes of my talk, and then I can dig into deeper technical issues that are perhaps hopefully going to be of interest to a broad audience as well. Okay, so what I'm going to do now, I'm going to tell you how we go about addressing convergence behavior and sample complexity of the random search method for LQR. So before I do that, let me just briefly summarize what allows you to establish linear convergence of gradient descent when you have model, even in the absence of convexity. And two properties of the LQR cost allow you to do that. The first one is smoothness over the sub-level sets of the LQR cost. And the second one is gradient dominance. Smoothness is very intuitive. It's a standard condition for objective functions that are twice continuously differentiable. You should think of gradient dominance as a PL type of a condition that relaxes standard strong convexity requirement in order for you to establish linear convergence. Namely, if there is a lower bound on the norm of the gradient, which is given in terms of the objective function difference between evaluated at the optimization variable k and the optimal value of k, then you can establish linear convergence even in the absence of convexity. And this was done for the linear quadratic regulator problem for discrete time systems recently by the University of Washington group, and we've done similar things for continuous time systems using completely different proof techniques that tap into control theoretic notions that I'm going to explain a little bit later. So with this in mind, I would like to move to model-free setup, and I'll come back to how we establish these properties and how we tap into standard control theoretic tools in order to do that. So what is a challenge in a model-free setup? The challenge is that you don't have access to gradients. You don't have luxury of evaluating exact gradients. Instead, you can only access random function values by perhaps running experiment or tapping into a simulation engine that perhaps domain experts have developed. They don't tell you what is under the hood, but they allow you to probe their simulation engine by giving, by passing to it current value of the feedback gain and a certain initial condition. And once you do that, you obtain a random value of your LQR cost, and the LQR objective function is obtained by computing expectation over random initial conditions, which we assume to be zero mean, unit variance, and with bounded sub-Gaussian norm. So we utilize random search method for model-free LQR, and what random search method attempts to do is to emulate gradient descent. Namely, you would like to do what gradient descent does, where again, you don't have a luxury to form exact gradient. Instead, the D here is a search direction that we are going to design strategically in order to estimate gradient using random function values. And when I say random search, I don't mean uninformed random search. We tap here into the area of zero order optimization or derivative-free optimization, and two techniques that are commonly employed to form search direction in the absence of gradients are 1-point and 2-point gradient estimates, respectively. So these techniques may remind you of a standard central difference from numerical analysis, and the difference between them is that in 2-point gradient estimation scheme, you assume that you can evaluate LQR cost for two different values of the feedback gain, but for the same initial condition. Whereas in 1-point estimate, you can only evaluate LQR cost at one particular feedback gain for one initial condition, right? Obviously, in applications, it may be more challenging to form 2-point estimates, especially if you're performing experiments, but if you have access to simulation engine, you can perhaps pass the same initial condition at the two different values of the feedback gain. And it is well known that these 2-point estimates have advantages in terms of reducing variance relative to 1-point techniques. What I would like to highlight is that you need to be careful in how you select these matrices U and the smoothing parameter R, where U, capital U is a random matrix that is uniformly sampled over sphere of a certain radius. And in our paper, we actually provide constructive techniques to choose both U and smoothing parameters so that you guarantee closed loop stability. Because if you don't have closed loop stability, your LQR cost may become infinite and these estimates may become meaningless, right? So these expressions here, they involve a single sample, but obviously in application, nothing prevents you from running multiple simulations for certain value of the feedback gain, but different values of matrices UI and different initial condition. This is going to give you your search direction and then your individual search directions, and then you can use mini batch gradient estimate to obtain your genuine search direction that you are going to utilize in your random search technique. And N is here number of samples, and the relevant question here is how many samples do you need in order to emulate properties of gradient descent, namely to achieve convergence rate that you have with gradient descent and with the desired accuracy. And this question was answered by Hessam in our recent work. here is probably the most important slide in my talk, where I summarize the main result. Namely, Hessa managed to show that random search method for the linear quadratic regulator in continuous time achieves a desired accuracy epsilon. Namely, it guarantees that a difference between LQR cost after t iterations, t here is not transpose, it's number of iterations, and the optimal value of the LQR cost is less than epsilon with high probability if the number of iterations is proportional to the logarithm of the reciprocal of the desired accuracy, right? If number of iterations is proportional to the logarithm of the reciprocal of the accuracy, you achieve desired accuracy epsilon, and this immediately gives you linear convergence. Actually, what is also interesting is that number of samples per iteration depends linearly on the number of components in your state vector. N is here, number of components that you have in your state vector, in your state equation. Let's say if you have standard mechanical system, let's say mass spring damper system, N would be 2, where state components may be position and velocity, right? And there is also this weak logarithmic dependence that obviously is of not significant importance. What I would like to highlight is that this constant C here depends on problem parameters. It depends on the initial condition, but it does not depend on the desired accuracy epsilon. And this is what differentiates our work relative to the alternative approaches, provided that you have a luxury of using 2-point estimates. Whatever I'm going to tell you today regarding our work is for two-point estimates. And then sample complexity is given by a product of these two quantities, obviously depends linearly on the number of components in your state vector and logarithmically on the reciprocal of the desired accuracy. Unfortunately, I don't have too much time to paint a very generous picture in terms of how our results compare to the state of the art in this literature, but let me draw your attention to an impressive paper that was published recently by UC Berkeley group, where they considered both 1- and 2-point gradient estimates for the random search LQR, and they quantified number of iterations and other properties. So one thing that they showed is clear advantage of 2-point gradient estimates compared to 1-point estimates, and this inspired us actually to closer examine 2-point estimates. What they showed in their paper is that with a single sample, you have polynomial sample complexity in terms of the desired accuracy, and you achieve sublinear convergence with a decreasing step size, right? With a decreasing step size. If your step size decreases as specified here, you're going to achieve sublinear convergence with a polynomial sample complexity. They also showed, actually confirmed results of the University of Washington group, is that if you use 1-point mini-batch estimates, you achieve linear rate with a fixed step size, but they significantly improved actually bounds on complexity relative to what University of Washington group had. They brought it down from 1 over epsilon to the 4th to 1 over epsilon squared. And again, both of these papers are impressive papers, and I would like to strongly encourage you to examine them. In contrast to us, they look at discrete time LQR problem, but you know, that's not the major difference between things that we do. The key difference actually in what we do is how to control how to make sure that random search method emulates gradient descent. And one way to do that is to attempt to control gradient estimation error. And this was the approach that was taken actually in these two papers. In contrast to that, we don't attempt to control gradient estimation error. What we do instead, we exploit the problem structure and we utilize state-of-the-art results in higher dimensional statistics to show that gradient estimates concentrates with high probability when projected to the direction of the gradient. Again, we utilize 2-point gradient estimates, and in contrast to these results that establish polynomial complexity in 1 over epsilon, we have logarithmic complexity. But the key differentiating feature, again, is that in our proof, we don't attempt to control gradient estimation error. We do what I already mentioned, and towards the end of my talk, I'll come back and tell you actually how we do these type of things. Now, what I would like to do, I'm roughly 25 minutes since the beginning of my talk. What I would like to do is to switch gears and to go back to a setup where you know model and to show you how you can establish global exponential stability of the gradient flow dynamics. And hopefully to the outsiders, to controls community, this is going to be a useful introduction in terms of what kind of challenges you run into when you attempt to use gradient descent or gradient flow dynamics in controls context. So the very first point that I would like to highlight is that once you express your LQR cost in terms of the feedback gain matrix K, you lose convexity. And you need to trust me that your LQR cost can be expressed by this expression here, where matrices K appear in this as this quadratic term here, but also matrix K appears in this matrix X, which determines the covariance matrix of the state vector of your system. And this is all done over the set of stabilizing feedback gains. If you don't have stabilizing feedback gain, your LQR cost is going to blow up. And the reason why LQR cost is a non-convex function of K is because in general, matrix exponential is not a convex function of its argument. And since matrix exponential appears in the expression for this covariance matrix, in general, you cannot guarantee convexity. Another reason, and another well-known fact from control theory, is that set of stabilizing feedback gains that guarantee stability of the controlled system. When I say stability, if you put certain excitations to your system, nothing is going to blow up, right? Either initial conditions or external perturbations, exogenous perturbations. Set of stabilizing feedback gains, which is always basic requirement in control of physical systems, is a non-convex set. So these are two reasons why you don't have convexity when you want to use optimization-based techniques and to work with LQR cost expressed in terms of the feedback gain matrix K. And what is our objective? We would like to analyze gradient flow dynamics that follows negative gradient with respect to the LQR cost expressed in terms of K, and to quantify, determine properties of this system. And we want to do the same for the gradient descent, where you should think of gradient descent perhaps as just a forward Euler discretization of the gradient flow dynamics with a fixed step size alpha. And just a reminder, in terms of global convergence properties for the gradient descent, they have been established by University of Washington group for discrete time systems, and we established similar properties for continuous time linear quadratic regulator in our CDC paper from last year. Okay, very good. So what are the key known properties? What are the properties that allow you to make some progress in spite of the lack of convexity? And two key properties that have been known for the last 35 years are listed here. First of all, even though you have non-convex objective function, there is a unique critical point. And the only critical point over the set of stabilizing feedback gains is given by the optimal solution of the linear quadratic regulator problem that you can obtain from the algebraic Riccati equation when you know model. Another property which we exploit, and which you can exploit actually in the analysis, is coercivity, meaning that as your feedback gain approaches the boundary of the set of stabilizing feedback gains or shoots to infinity, your LQR cost is going to blow up as well. And if you utilize these two properties, you can actually utilize objective error. You can use objective error as a Lyapunov function. Lyapunov functions are a standard tool in control theory that is used for studying stability properties of nonlinear dynamical systems. Namely, if you choose K to be in the set of stabilizing feedback gains, modulo optimal feedback gain, and you utilize coercivity, you can utilize the LQR cost, the difference between f of k and the f of k star, as a Lyapunov function. This Lyapunov function turns out to be positive definite and radially unbounded on the set of stabilizing feedback gains, and then show the derivative, dot here stands for derivative with respect to time, of this Lyapunov function, of this energy-like function, if you want to, along the solution of your gradient flow dynamics is negative definite on the set of stabilizing feedback gains. And it is a standard fact in control theory that these two properties are all you need to have in order to establish the asymptotic stability of a dynamical system. So based on the results that have been known for 35 years, and another property that we utilize here is compactness of sub-level sets of LQR cost, asymptotic stability almost comes for free if you tap into standard control theoretic results. This is really two-liner proof that is contained in our paper, but at least I feel that outsiders to controls community should be aware of these tools and of their power. Now, the challenge is, even though you converge asymptotically to an optimal feedback gain, the question is with what rate? And all heavy lifting or all hard effort has to be put actually in showing exponential rate of convergence. And as probably most of you with background in optimization know, a sufficient condition to establish exponential stability is given by a PL gradient dominance type of a condition. Namely, if you manage to show that your LQR cost satisfies this gradient dominance condition, namely, if you can establish lower bound on the norm of the gradient, where f stands for Frobenius norm, in terms of the function values, you can show linear convergence of gradient descent or exponential convergence in the context of gradient flow dynamics. And if PL condition holds, then actually you can show stronger result than what we listed here. Here you only establish the derivative of your LQR objective error of your Lyapunov function candidate is negative definite along trajectories generated by gradient flow dynamics, but here you can show not only that it is negative, but it's also proportional to the function value, where rho is this parameter that appears in the PL condition. And one example of this is given by a strongly convex objective function. If you have strongly objective function, rho would be nothing but strong convexity modulus. The challenge is that our problem is not strongly convex, and a question of how you establish that PL condition arises is a non-trivial question. University of Washington group has shown this, but their proof technique is dramatically different and way more evolved than ours. So what I'm going to show in the next few slides is how we show actually that LQR cost satisfies PL condition, and then consequently conclude exponential stability on the set of feedback gains. And the way we do that is by tapping into standard results in control theory. Namely, again, you need to take my word for this. You can rewrite your LQR problem as written here. You can rewrite it as a minimization of over matrices X and K, where K is a feedback gain that you would like to design, and X is covariance matrix of the state of your system that I listed a few slides ago. And this is LQR expression for the LQR cost in terms of K and X that I again listed a few slides ago, under the following two constraints. Second constraint is a little bit easier to understand. It amounts to stability of the closed loop system, namely positive definiteness of covariance matrix is equivalent, turns out to be equivalent to feedback gain being stabilizing, namely guaranteeing stability of your controlled system. And I say closed loop after you wrap feedback around it. This constraint is a little bit more interesting, and it is a constraint that is given by so-called algebraic Lyapunov equation that involves both feedback gain K and covariance matrix X. And everybody with background in optimization would be familiar with the fact that optimization, convex optimization, does not tolerate quadratic equality constraints. So source or non-convexity in this expression, in this optimization problem, is this bilinear or quadratic equality constraint. But if you stare at this expression long enough, you may notice that in addition to x, only product between kx and x enters, and perhaps one attempt to take care of this quadratic equality constraint is to introduce a change of variables. This is unfortunately a typo. This is not defined. It should be another way around. This dot should go here. This is what happens when you make changes at the very last moment. So if you introduce change of variables, if you call product between k and x, y, where this new matrix y has the same dimension as the matrix k, forget about these white spots here. They serve different purpose that I'm going to come back to towards the end of my talk. Then actually you can bring your problem into a convex form. And what I would like to highlight is that under closed loop stability, when x is positive definite matrix, you can go back and forth between y and k without any issues, right? So if you introduce change of variables kx equal to y, where y is now a matrix that has the same number of rows and columns as k, and x is a positive definite matrix, you can actually rewrite your linear quadratic regulator problem in the following form, where you no longer have quadratic equality constraint, but you have this linear equality constraint. And it turns out actually that this objective function, which now I called h, is jointly convex in x and y. Right? This is not, though, what is typically exploited in controls literature. If you take a look at what control theorists typically do, they utilize Schur complement in this expression and bring this characterization into semi-definite programming characterization, and this is an excellent reference on the topic along with many others. So the way you should think of this characterization is a dual to algebraic Riccati equation involves controllability Gramian of the closed loop system, which is given by x, rather than observability Gramian of the closed loop system, which is given by p. Lots of buzzwords, but perhaps for students or newcomers to controls community, this terminology may be useful as you continue moving forward. So what do? We don't go into SDP characterization. What we do instead, we express x in terms of y, and you can do that using this linear relation here. It turns out actually that x is an affine function of y. This positive definite constraint reflects closed loop stability, and a and b are just curly a, or calligraphic a and calligraphic b are just linear operators that act on x and y respectively. And then once we do that, we write LQR cost as a convex function of y, which we call h. Right? Namely, if you use composition rules for convex functions, you can show that h is a convex function of y, which is nice. Now, at least, you know, we made some progress. We made this problem that appeared hopeless early on a little bit more tractable. And what we would like to do, we would like to examine gradient flow dynamics over the convex landscape, where rather than computing working in k coordinates, you work in y coordinates, right? And then based on, I'll tell you how we relate this actually to the gradient flow dynamics if you do it in the original set of coordinates. Right now, the key question is, what are the properties of these dynamics? I already told you that you have convexity, but you have even more than that. In fact, what Hesse managed to show is that h of y is a strongly convex function of over the sublevel sets that I'm going to specify in a moment. And one way to show it is to write down Hessian. It turns out that Hessian is given by Frobenius norm squared of this expression here that depends linearly on the matricial variable g. So this tells you immediately that you're greater than equal than 0, but what Hesse managed to show is, in fact, an existence of a positive constant rho, which depends on the initial condition, so that you have this lower bound, and this amounts to strong convexity in this particular setup. What I would like to highlight is that this set S tilde of A determines sublevel sets of the function h, where y is a matrix which has m rows. M is the number of components in the control vector, and n columns. N is number of components in the state vector. You need to have closed loop stability, and then sub-level sets are determined by this value of A, which would be specified by the initial condition. So based on this, essentially, exponential stability, since you have strong convexity, is immediate, as I already argued. In fact, for any initial condition which belongs to this set S tilde of A, not only do you have exponential convergence in the objective value, but you can easily show actually that your optimization variable Y converges exponentially. And again, all of these things are fairly trivial if you're comfortable with strong convexity properties. This is all great, but does not answer our question. It does not answer our question, what are the properties of the gradient flow dynamics when you actually compute K using differential equation where the generating direction is given by a negative gradient of the original objective function. And the way we answer this is I think, pretty interesting, and I'll guide you through that. So what we want to do, we would like to relate essentially convex and non-convex landscapes, convex in Y coordinates, non-convex in K coordinates, right? And how we relate them is what I plan to tell you in the next couple of minutes. What Hessam did, he utilized induced trajectories, namely, if you don't follow gradient flow dynamics on K, but you use Y to compute corresponding control variable by first computing X and then using this expression, then convergence over these induced, exponential convergence over induced trajectories is trivial. It's immediate based on the properties, based on the equivalence of the objective functions in Y coordinates and corresponding in induced trajectories. So now the key question that arises, and a bit of geometric picture is provided here, is whether we have exponential convergence for the original gradient flow dynamics, which moves actually your optimization variable towards the level sets of the LQR cost in a normal direction, whereas this induced trajectory does not do it in a normal direction. You have exponential convergence. Here the question is whether you have exponential convergence or not. And the way we did this is by essentially combining both angle and magnitude information and utilizing projection of the induced direction to the direction of generating direction in the original coordinates. And what Hessam again managed to show is that for any feedback gain that belongs to the set of stabilizing feedback gains, to these sub-level sets, the Frobenius norm of the generating direction, where K dot is given by a negative gradient of the original LQR cost, is lower bounded by a Frobenius norm of a projection of the induced direction to K dot. And this C of A is a positive constant that depends on the initial condition and problem parameters, and the SA are sub-level sets of F. Combining these two properties, actually combining strong convexity of age and previous property, you can establish gradient dominance. And what I would like to highlight is that in gradient dominance, both strong convexity parameter for the function H and this parameter C from this expression appear, and finally show exponential stability of the original gradient flow dynamics. You need to work a little bit harder to show that even in the optimization variable, you have exponential convergence, but Hessam has shown this as well. And once you want to go to gradient descent, the challenge is how to determine step size. There, in addition to PL type of a condition, you need to have smoothness, standard fact from optimization. Again, Hessam managed to quantify smoothness factor and to establish linear convergence with a fixed step size that is determined by PL parameter, if you want to, smoothness parameter, and this parameter C that is listed on the previous slide. So with this, I'm pretty much done with convergence of gradient flow dynamics, properties of gradient flow dynamics, and gradient descent. What I would like to do now is to go back to random search method and just to give you a bit of intuition how we go about proving things there. I'm 44 minutes after I started. Hopefully, I'll be done in a few minutes, and then we'll have plenty of time for questions. So now back to random search method. So what do we do in random search method? Rather than utilizing gradient descent, we utilize approximate gradient descent. And again, this is a standard fact in optimization that approximate gradient descent with the search direction D would converge to the optimal point if these two conditions are simultaneously satisfied. The first condition, both of them have interesting geometric interpretation. The first condition quantifies the half space, and the second condition determines sphere. And essentially what this condition is telling you that the projection of the search direction into the direction of the true gradient should not become too small as measured by the norm of the gradient. And the second condition tells you that essentially norm of this approximate search direction should not become too large as measured by the norm of the gradient. And theta 1 and theta 2 are parameters that appear in a expression for the fixed step size. Mu here plays the role of rho in the previous expression. I apologize for switching notation here. So in this, again, all holds in deterministic context. The challenge that you face when you use random search method is to show that to essentially recognize what kind of result you can establish in a probabilistic setup. And what Hessa managed to show is that these two relations here hold with high probability when you utilize random search method. And rather than going into to form D, to form the search direction D, approximate search direction D, and rather than going into details, let me just give you an example. This is a mechanical system which contains a number of masses with inverted number of cards with inverted pendula on them. Each of these subsystems has 4 state variables: position, perhaps, and velocity of the card, and angle and angular velocity of these pendula. And you can control each card using force control. And the question that we wanted to address here is how to design linear quadratic regulator using random search method in the model-free setup, where we only have an access to simulation engine around certain operating point. And just to give you a bit of indication of what kind of results you obtain, I'm showing here 2 expressions that I listed 2 slides ago. So these are essentially equivalent expressions to these expressions here. And these are histograms, essentially, for 10,000 experiments that we ran. Both horizontal axes show parameters theta 1 and theta 2, and vertical axis shows number of occurrences when these expressions are equal to theta 1. Or equal to theta 2. And if you choose theta 1 and theta 2 carefully, in this case 0.1 and 35, with overwhelming probability, you have these two events holding. And the last thing that I want to show you is a linear convergence curve. Our results nicely demonstrate linear convergence, and in contrast to most stochastic techniques, we have smooth convergence curves without actually any typical oscillations and large variance that you typically see in this context. So with this, I'd like to wrap up. I just want to tell you about a couple of things that we are currently pursuing. A topic that is very close to my heart, and that I would like to see how far it can be pushed in the context of model-free reinforcement learning techniques, is design of sparse feedback gains. The motivation for this is to reduce communication burden, perhaps between different subsystems. If you think of let's say U3 here as a control action that acts on a subsystem 3, if these two elements in the feedback gain matrix are equal to 0, then you would only utilize information from the subsystem on which you act and two neighboring subsystems to form control action, right? And this is an important challenge in distributed control. These are way more challenging problems because they are typically non-smooth, and unfortunately these standard changes of variables that I listed before are no longer going to work because it is very difficult to, let me try actually to illustrate this. It's very difficult to relate sparsity pattern on K on sparsity patterns on X and Y. Unfortunately, you can't use standard changes of variables to take care of these problems, and you run into non-smooth optimization problems as well. And then another important challenge is output feedback reinforcement learning, where rather than having access to the state measurement, you only have limited noisy measurements that are given perhaps by linear combination of states, and you would like to design dynamic controller rather than state feedback gain using reinforcement learning techniques. With this, I'd like to list important references, groundbreaking work by UW and UC Berkeley groups, and our papers. What I would like to highlight is that whatever we established for continuous time linear quadratic regulator in terms of performance of random search method, everything holds actually for the discrete time problem as well. And this is upcoming Control System Society letters publication, which is going to be presented at CDC in December as well. Archive preprint that I need to update. We resubmitted this revised version was submitted more than a month ago. I still haven't updated this. I'll use this as a motivation to do it as soon as possible, and our CDC and L4 DC papers. The most important slide is to thank Hesam for his phenomenal work, and for Armin and Magdi for being outstanding collaborations, and obviously without sources of funding, none of this would be possible. Thank you so much for your attention. I apologize for going slightly over 50 minutes, and I'll be happy to answer any questions that you may have.
Great. Thank you, Professor Jovanovic, for the great talk. And as for the question, Yung Chao asks, I guess you have addressed this question partially during the talk. So the Yung Chao's question is about if the optimal controller has some sparsity pattern, is it possible to design some algorithm that utilize such a pattern? Yeah.
So it's a very interesting question, actually. First of all, there are many different layers to it, and you know, to a large extent, you can tap into results from the area of compressive sensing and related fields, and this is what we've done in our work for the setup when you have models, right? First of all, the natural question that arises is what should be a sparsity pattern so that you guarantee certain level of performance. Let's say as you start dropping certain elements from your feedback gain matrix, how much performance are you going to compromise along the way, right? And there, obviously, this is in general intractable combinatorial problem, but you can utilize L1 type of regularizers to come up actually with parameterized family of sparse feedback gains that gradually deteriorate performance relative to the optimal centralized. This is one side of the coin. Another side of the coin is if you say, hey, look, I can only afford to have tri-diagonal feedback gain matrix where I communicate only to my nearest neighbors in this mass spring damper system that involves pendula as well. Let's say if I can only use measurements from nearest two neighbors, that would immediately lead to a tri-diagonal structure of your feedback gain. And then the question is, you know, how much performance do you compromise along the way? It turns out actually that if you do this strategically, you can achieve decent performance even with these distributed control techniques. But again, none of these standard techniques apply here. So there are no guarantees actually that you're going to converge to the optimal feedback gain in contrast to linear quadratic regulator. So this is an open question, especially in the context of RL. It's an open question even when you have a model. So all of these things that we managed to show, right? First contribution in my talk. Let me go back here. So this is an open question here, right? If you give certain sparsity pattern, and this would enter as one additional constraint, or if you use L-band regularization, you can use proximal gradient, for example, proximal gradient flow rather than gradient flow. Are you going to converge to the optimal feedback gain? This is unknown even actually when you have a model. So lots of interesting things to be done here, even in the setup when you have a model in data-driven and model-free setup. Obviously, it's even more exciting than that.
Okay, thank you. And then another question maybe is that the anonymous attendee would like you to elaborate more on the output feedback setting, that is the output LQG, and what about some of the recent progresses and the challenges of this setting?
Yeah, very good. Excellent question. I think that would be a next natural step, right? I mean, it would be a natural step to bring this into observer-based type of controller, and there have been exciting things that have been going on in this domain. But generally speaking, this is an open question. Again, it's a little bit, even what we've done here is to some extent cheating, right? I mean, we know what the optimal feedback policy is, and then we say, let us restrict attention to this. Imagine now you want to design dynamical controller, and obviously for linear systems, separation principle holds, linear quadratic Gaussian allows you to design observer gains and feedback gains separately. You can utilize that structure and say, can I learn K, feedback gain, and L, observer gain, using RL type of techniques, using policy optimization if you want to, right? But imagine that you didn't know what the structure is, and especially in the output feedback setup, controlling so-called non-minimum phase systems is a non-trivial challenge. This challenge does not arise when you have access to all state variables. The genuine question that I'm interested in is, if we don't use this prior knowledge that this should be observer-based controller, how far can we go with this? I'm not saying that, using this knowledge makes your problem dramatically easier. It may turn out to be actually, it is still a difficult problem, and, these challenges should be settled. But generally speaking, if control theorists haven't spent last 60 years answering fundamental limitations for problems that are difficult to control, non-minimum phase dynamics and things of that sort, how far can you go with your RL type of techniques, especially when you bring them into an online environment where safety is paramount? So there are lots of interesting things. Again, I'm not going to do justice to all exciting papers that have appeared in this context, but lots of interesting things to be done and to consider.
Mm-hmm. So maybe to follow up this question, I was wondering, suppose we are given a say common filter which enables us to learn the belief state given the observation, then is it possible to run a policy-based optimization algorithm? Yeah,
I mean, sure, of course, right? I mean, the difference would be that you would replace this state vector with an estimate, right? And again, the only question is what gives you luxury of computing Kalman gain, and on the other hand, you can compute feedback gain, right? So to me, it would be more natural to pose this as a joint design problem over both K and L, and you can certainly write necessary conditions for optimality and form gradient and see what comes out of it. In fact, I've done this in the context of designing sparse feedback gains and sparse observer gains. But some interesting interplay between them happens there. Setup that you mentioned is way more tractable when you fix one of them and you want to design the other, then joint design of them. Even though separation principle holds, you need to be a little bit careful, how you disentangle different things along the way.
Thank you. And another, the last questions are concerning about the random search algorithm. So the first question is about how to choose the step size. Is the step size fixed or is independent to the accuracy level epsilon?
Yeah, excellent question. I mean, actually, step size is fixed. Step size is fixed. It does not depend on epsilon. But again, the problem is that step size depends on initial feedback gain and model parameters. We don't know model parameters. So what Hessam has done in these computational experiments, he used backtracking, essentially to Armijo rule type of a technique to guarantee stability and to come up with step size. Even though we quantified, we confirmed the existence, we proved the existence of a fixed stabilizing, fixed step size that guarantees linear convergence, as I mentioned here. What I would like to highlight, step size does not depend on desired accuracy, but depends on problem parameters. And if you don't know problem parameters, obviously computing these things, you have additional burden. So he utilized backtracking in his computational experiments.
And the last question is that in your talk you illustrated that the random variable u and the parameter r is chosen such that the random search also ensures stability, feedback stability. Yes. I was wondering what characteristics of the LQR is the choice of this random variable u hinges on. So how to choose the distribution of u?
All details are again in the paper. It's been a while since, to be honest with you, since I looked at this. But Hessam very carefully actually develops careful conditions for this. If he's online, maybe he can chime in and provide additional information. To be honest with you, it's been a while since I looked at this, and I try to keep bigger picture in mind rather than go into these details. But Hessam, please chime in if you're online.
He is online. Shall I promote him to panelist?
Sure.
Then we'll if you here he is. Excellent. Hessam, please.
Right.
His voice is not on.
Yeah, he's mute.
Hessam, you need to unmute yourself. So if you can unmute yourself and maybe maybe he wants to stay muted. Maybe he's pleading the fifth. Maybe I should have done the same. Maybe I should have hugged everyone in the virtual world and declared victory. Just kidding. Hessam, are you alive?
He said yes. Let me type here.
Oh, he doesn't have a Mac.
Oh, okay, he is trying to find them.
So look, we'll again, all details are in the paper, but send me an email and then we'll answer this. It's no effort really for us to do that, but everything has been taken care of in the paper.
Thank you.
Okay, good. Anything else?
That's all the questions I have. Thank you again, Professor.
Thank you so much, guys. This was lots of fun, and I had a blast. Stay strong, and hopefully I'll see some of you in real life sooner rather than later.
Thank you. Looking forward to seeing you soon.
Thanks a lot, guys. Bye now.
Thank you.
Bye. Also, thanks everyone for joining today. We will see you next week. Bye.